Yes, thank you. Okay. Here, see, uh, electrical network transfer functions. Actually, there are three things. Consider passive components, passive linear components. Okay. Passive linear components like resistor, capacitor, and inductor. So how many passive components are there? Three components: resistor, capacitor, and inductor. Okay, remember this. There are three passive components: resistor, capacitor, and inductor. Okay, and we'll summarize the relation between them, like according to the voltage and the current, and between voltage and the charge. Voltage and charge. Voltage and current, and voltage and charge. Two things. Voltage and charge, and voltage and current. Okay. So we have these two things. Summarize the components and the relationships between voltage and current and between voltage and charge under zero initial condition. Okay, just remember this. Resistor, capacitor, inductor. We are considering these three. These three are the passive electrical component. Okay. Now see that table. This table is important because if you understand this table, then you can solve the mathematical problems very easily. Okay, let's explain these all things one by one. That is the capacitor. First one is the capacitor. I think you know the symbol. You know symbol, capacitor symbol, resistor symbol, and the inductor symbol. Now see the relations. Which relations we are considering, like voltage current relation, current voltage relation, voltage charge relation, impedance and admittance relation. So see, what is the voltage current relation? It is the relation of the voltage current, and for the capacitor it is the current voltage relation. See, it is integration and it is the differentiation, and it is a voltage charge relation, and it is the impedance. V impedance is equal to Vs by Is, so 1 by Cs, and admittance Ys is equal to Is by Vs, so that is the Cs. That is in the frequency domain. It is frequency domain. It is not the time domain. It is frequency domain. Okay. And the resistor Vt is equal to Rit, and It is equal to 1 by R into Vt. And voltage charge are dqt dt, and impedance only R, and admittance 1 by R is G. And that is the inductor relation and current voltage relation. That is the voltage current relation. See, this is voltage, this is current. That is current, that is voltage. And that is the voltage charge relation, impedance relation, admittance relation. Okay. The following set of symbols and units is used throughout this book. You can see they use for the voltage the unit is volts, we know that, and for the current it is amps, ampere. For the charge it is coulomb, and for the capacitance it is farads. For the resistance it is ohms. For the conductance it is mohs, and inductance for the henries. These are the relations. Okay, we'll use these relations in the maths. That is the important. We have to solve the maths according to these relations. Okay. Is it your first week or is it your second week or third week? Second week or third week?
Third week, sir.
Third week. Okay, so I think you need to give a. I think you can give a class test or some test, something like that, like some viva. Okay, something like that. Not the regular one. I'll check your condition between the class. Okay, I'll ask you and you'll tell me the situation. Okay, do you understand or not? Okay, because I think since it is third week, So your midterm will be conducting soon, right? As well as one thing, as I discussed before, you had to give a presentation. Okay, so when it would be better to give a presentation? After the meet or before the meet?
After the midterm.
After the midterm. Okay, no problem. So you will give the presentation after the midterm. Okay, and yeah, and you know the midterm condition, like the 10-mark quiz and the 10-mark viva, right? That's why I'm not taking another quiz here, since I'm taking one quiz for the midterm. Okay, instead of this, I'm taking the presentation. This presentation skill is very important for you guys, because when you pass the course or when you pass the program, then you will regret this. Okay, so let's look at the first problem. Example 2.6. It is very important because if you know the first one, then remaining one will be very easier for you. Okay, so let's look at the problem here. See, the question is, find the transfer function relating the capacitor voltage. Find the transfer function relating to the capacitor voltage VCS, say VCS, and the input voltage Vs. So transfer function will be, what would be the transfer function? VCS divided by Vs, right? Output divided by input, right? Output divided by input, that is the transfer function. Output voltage divided by input voltage. Actually, it is the Fourier transform, Laplace Fourier transform of the Laplace transform of the output voltage to the Laplace transform of the input voltage. That is the transfer function. That is the transfer function of this system, this circuit. That is the transfer function. Remember, what is the transfer function? Transfer function is the output by input. That means output of the anything at the Laplace transfer form. Okay, LT form. LT means Laplace transform. Okay, so remember this one. Okay, now see this circuit. Let's look at the circuit. That is a RLC network, right? RLC network, and here is a VT. That is the input voltage. The input voltage, that is the actually the AC. And here is the L means the inductor, R means the resistance, and C means the capacitance. We know that things. So we can our first priority would be to change this one. We can change. How we can change this? Let's look at here. How we can change this thing? We can change this one like this. That is plus, that is minus. CVS. We have changed this one. L is here, R is here, C is here, and VCS. VS and VCS. Okay. Find the transfer function using the capacitor VCS and VS. So at first of all, we'll change this one. Okay. Now let me clear this drawing. Okay. So we'll apply the, what will apply? We'll apply the KVL, right? Summing the voltage around the loop. voltage around the loop. See, VT is the summation of all three, right? So at first of all, L dit dt. See this one. Voltage current relation, inductor L dit dt, right? Voltage is equal to L dit dt. Voltage is equal to L dit dt. R, for the R, what is the relation? RIT. For the R, it is the RIT. And for capacitance, this one. See, we have found these things from here, from this table. So you need to memorize this table. It is very important. I cannot give you the table all the time, but you have to remember these things. Okay, see, is equal to VT. Now what they have changed? Changing variables from current to the charge. See here, current to the charge. We know that current is equal to dqt dt. ddt of qt, charge per unit time. dt of qt is equal to the current. ddt of qt is equal to the current. See, the charge per unit time is equal to the current. So we have changed this one. Say, instead of IT, if I write ddt of qt, then it would be d square qt dt square t, right? And IT, instead of IT, I can write this one, ddt of qt, and instead of IT, if I write this one, 1 by c, so instead of IT, if I write the ddt of qt, then the this differentiation and the integration will cancel out, and as a result, qt will be there and vt is there. So it is our changed form. Now we can change the qt. See here, qt from the table 2.3. What is the qt? Let's see. Instead of qt, we can write what? CVCS, CVCT, right? Here, instead of qt, we can write what? We can write the CVT or CVCT. VCT means the capacitance voltage. Okay, and the final one. So instead of qt, you can write the CVCT. Now put this ones, put this value. Instead of qt, put this value in the 2.62. Then you will get this one. Okay, then you will get this equation. Then you will get this equation. That is the now from this equation we will change this equation to the Laplace transform. Now important thing, how to change this one. Let me help you. Okay, so we have to change this equation 2.64 into the Laplace transform. We have to change this one into the Laplace transform. So see, d square, that means s square. So if we change, then LC s square capital VCS. That is the first one. First term. For the second term, RC will be there. D dt of VCT, that means S. VCT, that means VCS plus VCS is equal to VS. Okay, something like that. So your equation will be like this. If we change this one to the Laplace transform, then what you will do? You will take the common, VCS common. Take the VCS common. Then LC is square plus RCS VS plus 1 is equal to Vs after taking the Laplace transform. Now we know what? Output by input. So output VCS divided by input Vs, and as a result we'll get the LCS square plus RCS plus 1. C. That is our final output, the final result. That is our final result. And so we have found the transfer function. We have found the transfer function according to the requirements. Okay, according to the requirements, we have found the transfer function. So we can see this one. Let me clear. See, just what I have done. Now finally they did one thing extra, like S square, so just divided by the 1 over LC. Finally, that is the block diagram. This is the input and this is the output, and this is the transfer function. See, it is the open loop control system. Block diagram of a series RLC electrical network, which is an open loop control system. Okay, see this. So solving for the transfer function visible Vs, we obtain this one. So that is your open loop transfer function output. Okay. So do you understand the math?
Yes, sir, we understand. Except 2.62.
Yeah, 2.6, 2.6. That is the your math. 2.62, right?
Yes, sir, that line.
Okay, that line. How it comes? See this. Okay, let me write something. LDITC. LDDT. Okay, instead of IT, we'll write the DQTDT. DDT of QT. Okay, plus RIT. That means R DDT of QT. Now this one plus 1 by C. See this 0 to 1 instead of IT, you can write the DQT dt, and which is there. Okay, now we can write this one L d square dt square qt plus r ddt of qt plus 1 over c. See, this is dt and this is also dt. So integration and differentiation, as a result only qt will be there. Okay, and the dt. That is the expression of the 2.62. Okay, just replace the IT to the ddt of qt. Nothing else. Replace the IT. Replace the IT only. Here, replace the IT, then you will get this one. Okay. Now, so finally, see this. Now I will explain this line also, so that you will understand very well. Like see, like what we have got the VCS by VS, VCS by VS is equal to 1 by LCS square plus RCS plus 1. Now 1 by LC divided by 1 by LC. So what you will get, 1 by LC into LCS square plus 1 over LC into RCS plus 1 over LC into 1. Okay, so we'll divide both terms by 1 over LC. Then what we'll get, 1 over LC will be there, and LCS will be cancelled out. It would be S square plus here R by C will be cancelled out. C will be cancelled out. R by L into S plus 1 over LC. So that is your output. Okay. That is your output. So finally, what we will get? We will get this one. So we can finally write as a block diagram. VS, that means the input. VCS, that means the output, and here the transfer function. So that is your open loop control system. Sorry, open loop open loop well control system. Okay, so that is your answer of this one. So I think this one is clear. This is initial math, interesting math. Okay, I think you'll be able to solve it. This kind of problem, I think you can easily solve. Okay, I hope.
Yes, sir.
Right, easier. It is easy, but easy thing will not come in the exam. Okay. Now let's move on. Let's move to the next one. Okay. The guy who are in that Dhaka, you can buy the book. Okay, it is better to buy the book, or you can go to the not library, not now, but you can buy the book. Go to the Nilkhet. Okay, you'll get one. A nice book. It is very important for your future also. Okay, this book, Norman is nice, control system engineering. Okay, now a few things. For the capacitor, Vs, let us now develop a technique for simplifying the solution for future problems. First, take the Laplace transform of the equation in the voltage current column of table 2.3, assuming zero initial conditions. See, the Laplace transform. Just remember these terms. These terms will be useful in the next maths. Okay. Vs is equal to 1 over Cs into Is. That is for the capacitor, and for the resistor Vs into Ris. For the inductor it is Ls into Is, and for the transfer function Vs by Is into Zs. Okay, so remember this term. We'll use this term directly into the figure. Okay, so we'll use this term directly because we do not want to uh, lose our time. Okay, we'll use directly. Now, okay, so let's look at this 2 point. So how we'll change this directly? Redraw the original network showing all time variables such as VT, IT, and VCS as Laplace transform, VSIS and VCS respectively. See, first of all, when you'll get the figure on the question, then change it to the new thing. Okay, redraw the original network showing all time variables such as VT, IT, and VCT as Laplace transform, VS, IS, and VCS respectively. Replace the component values with their impedance values. Components values with their impedance values. That is the important. Just change the component value to the impedance value so that you can easily solve this one. This replacement is similar to the case of DC circuits, where we represent resistors with their resistance values. Okay, now they will do that example 2.6 again, this new method. Okay, so this time we will not do the differential equation, rather we will completely use another thing. See how they did this. I think we remembered the RLC network, right? Do you remember it? Simple RLC network. That is the simple RLC network. Okay, like this. My drawing is very bad. Okay, using figure 2.5 and writing a mesh equation using the impedance. Okay, now let's go to move on the figure 2.5. Where are that? Okay, that is the figure. Okay, see here. Instead of VT, small one, instead of VT, we have write the VS, and instead of BCT, we have write the VCS. Okay, LS and RS. Instead of inductor, we write the LS. Instead of R, we can write the R, and 1 by CS instead of. So that is the impedance value, right? These are the impedance value of inductor, of the resistance, of the capacitor in terms of frequency domain of the Laplace transform form, in the Laplace transform form. So we just completely transformed the previous network to the Laplace transform network. Okay, we have changed this. So whenever you will get the circuit like that, just you change it, change the circuit. Instead of inductor, you write the LS, and instead of resistor, what happened to some of your friends? They are joining again and again. I think something wrong with their network. Okay, so that is the thing. We'll use this one, the VS, LS, R 1 by CS and IS. Okay. Now what they did, just okay. Let me show from that one. Here what we'll do, we'll apply the KVL, right? Kirchhoff's voltage law. So VS, we know the VS, LS, into IS, LS into IS plus R into IS plus 1 by CS. Just a minute. Here, just look at here. LS into IS, R into IS, 1 by CS into IS is equal to VS. Okay, same equation. We can write this equation. Now, what is the output? Output is the IS by VS. So put this one IS by VS. So that is the your same equation, right? Same equation. You will get the same equation. But here something else are there. But the voltage across the capacitance is the product of the current and the impedance of the capacitor. Thus, VC is equal to IS into 1 by CS. Clear? That's why we can write the IS. Voltage across the capacitor VCS is the product of the current and the impedance of the capacitor. So we can write VCS equal to IS into 1 by CS. Okay. See, same thing will happen. So you will get the same result one by one whenever you do this. Okay. And some other examples are there. So you can skip this one via voltage division. No need, same thing again. Now complex circuits by mesh analysis. It is important. Mesh analysis is important. So after completing the mesh, I will close the class. So mesh is important. Let's look at the mesh analysis. Okay. So do you know what is the mesh? I think you have already studied the mesh analysis, right? I think you have studied the mesh analysis before. So here they say that how to perform mesh analysis. Replace passive element values with their impedances. So replace the passive element. What are the passive elements? Resistor, inductor,
Capacitor.
and
Capacitor.
capacitor. Right. Remember, what are the passive elements? Just do remember. Okay.
Okay.
Because it is as an electrical engineer, you should understand what are the passive elements. Okay. You should memorize the name. Okay. Now, the second part. Replace all sources and time variable with their Laplace transform. Now replace the sources, that means the current source or voltage source or whatever it is, and time variables with their Laplace transform. Just replace this according to the Laplace transform. Assume a transform circuit and the current direction in each mesh. Now, and you will have to draw the current direction also. Okay, otherwise you cannot do the mesh. And write Kirchhoff's voltage law around the each mesh. And KVL, apply the KVL and solve the simultaneous equations for the output from the transfer function. Let us look at an example. Okay, transfer function multiple loop. See this figure. Try to understand this one. Try to understand this figure. How many loops are there? Two loops, right? There are two loops. There are two loops. 1, 2. Now, what is our first job? What we have to do? Our first job is to replace this one, this one, this one, this one, and this one according to the Laplace, right? According to the Laplace transform. So according to the Laplace transform, what we will do? Instead of Vt, we will write the Vs. And instead of Vct, we will write the Vcs, but we can use the 1 by Cs also. And For the L, we can write the ls, and here another term we'll use VLS. Actually, VLS is the inductor voltage, and here is the R1 is the R2. That is the VCS, the capacitor voltage, and it is the inductor voltage. I1 is the current, I2 is the another current. Right? Two currents are there, I1s as well as the I2s. So first thing first, we change the form, we change the circuit diagram to the Laplace transform diagram. Now we will do the math. Okay, first loop, apply the first loop and the second loop. We will get two equations. Let me explain it to you. Here, the first equation. That is the loop 1. This one the loop 2, right? Loop 1 and loop 2. So what we'll get here? For the loop 1, Vs is equal to R1 I1s, right? R1 I1s for the loop 1 plus Ls I1s minus Ls I2s. That is the first loop. And the second one, for the second loop, it will be 0 here because we'll use this term inside. For the second loop, let's say ls, not ls, let me write according to thing, R2 I2s plus ls I2s plus 1 by cs I2s minus ls I1s. Right. So that is your equation, these two equations. Just apply the mesh here. Apply the mesh here, then you will get these two equations. Okay. So that is, these two equations are there according to the mesh. Okay. The common term, this is the common term, right? Common term is the ls. So when you consider this loop, then it will be positive for the I2, and here it will be negative for LSI1s. Okay, two things. It will be negative for the common loop. Other things will be as it is. Now, now you have to do some other works. Now write these two equations like this way. That is the first one. Common the I1 term and the I2 term. The second, similarly, common take common of the I1 and take common as the I2. When after taking the common, now you can apply the Kramer's rule. Where at the Kramer's rule? Let me show you. See appendix G. Okay, let me go to the this thing. Would you like to change to no? Have you seen page in the Would you like to change about okay, let me see. Control system engineering, see 8th edition is there. Okay. Okay. Now, according to the Kramer's rule, I2S, now this one, whenever you consider the I2S, then write the coefficient of the coefficient of the first line here, coefficient of the first line here, but do not consider the I2S. R1 plus LS, R1 plus LS and the VS, and the minus LS and 0 divided by delta, or the just cross multiplication. This is 0, minus into minus into plus, so it is the LSVS divided by delta. And what is the delta? Delta is the like this, R1 plus LS minus LS minus LS plus R2 plus 1 by CS. Okay, now you can form the transfer function I2S divided by VS. Why I2S by VS? See, that is the output, right? I2 is the output and not the I1. It is input and it is output. So I2S by VS is the your equation. So I2S, instead of I2S, put this one, and instead of VS, just put the VS. So VS will be cancelled out. It would be LS by delta. So you can write the delta also, multiply this and minus to minus. Okay, just do the simple math, then you will get this. Okay, so that is your final equation. So
And 2.8 there.
which one?
2.8 T.
2.82 or 81?
2.80.
82. Okay,
80, sir.
80. Oh, this one.
Number B, sir. B.
B. This one.
Yes.
Oh, this one simple one. Just take the common, like here. He, what you can write here in this equation. If we consider the I1s, so minus LS I1s, and what are the I2s? LS plus R2 plus 1 over CS, that is the I2S, that is the 0, like this. And here the first one, here we can write like this, R1 plus LS, just take the common, I1S minus LS I2S is equal to VS. See, that is the way.
Yes, sir.
Just take the common, nothing else.
Yes, sir. I'm listening.
Okay, and when you consider the I2, whenever you consider the I2S, it's I2S, when you consider the I2S, so just do not write the coefficient of this I2. In that case, you write the coefficient of I1s. So R1 plus LS, here this is the VS, and here minus LS, and here the 0, and delta. Now the equation is just cross multiplication, this one this, and then this one this. So that is 0 minus LS into VS. Okay, divided by delta. So equation would be LS VS divided by delta. Okay, like this. And for the delta, the equation would be like this. Okay, see this. For the delta, what is the equation? Just they have taken this coefficient. They have taken this coefficient into consideration. Okay, so that is the way you can write this one. Now see, they summarize here. Summarize the equations here. Sum of impedances around mesh 1 into I1s minus sum of impedances common to the two meshes minus I2s is equal to sum of applied voltages around mesh 1. And for the second line, minus sum of impedances common to the two meshes into I1s plus sum of impedances around mesh 2 into I2s. And sum of applied voltages around mesh 2, this is the second one. Okay. So that is the mesh equation, how to solve the mesh. Okay, they have used the nodal equation also. We'll see this to the in the next class. Okay, but mesh are important. Let me show you another one. See this one. This is the mesh equations by inspection. Example 2.13. Example 2.13. This is the mesh equations. Write but do not solve the mesh equations for the network shown in the figure 2.9. So you do not need to solve, just you can write the equations. So see this, it is already given. Okay, you do not need to solve this kind of problem, but you can write the equations here. So how they did this? See the figure. Now you can write the equations. Let me write the equations for you guys, for your betterment. The first one, let me write you the equations I1. So I1 is see here value is 1. Actually 2 I1s, because 1 plus 1 is equal to 2 plus 2s I1s 2s I1s minus here two things. For the I2s you get this one minus minus I2s, since it is 1 minus 2s I2s and minus I3s is equal to Vs. That is the first one. That is the first equation. So if we take it, make it simple one, 2 plus 2s into I1s. Okay, something like that. Uh, in this matter, they have write the equations. See, that is our first equation, then that is our second equations, that is our third equations. Just write the equations and do not solve. They did this. Okay. So that is the thing. Uh, so it is our equations. Say this. These three equations, which can be solved simultaneously for any desired transfer function. For example, I3 is by Vs plus. We can solve it, but we are not considering this one right now. Okay. But we are only taking the equation, solving the equations only. Okay. Sum of evidence common to mesh 1 and mesh 3, sum of evidence common to mesh 2 and mesh 3, and sum of evidence around mesh 3. Okay, like this. These are the equations, mesh equations by inspections. Okay, so for the theory, I am closing this theoretical part today. Okay, we have what we have studied so far today. We have seen the mesh equations, and we have seen the normal equations, right? And few things are there also remains. So I have skipped those things, nodal term, but we can check in the next class, inshallah. No problem. Okay, first of all, what we have learned from the 2.6 and from the 2.7. From the 2.6, we have learned that transfer function single loop by differential equations. We can solve the maths by differential equation, as well as we can solve the math using the single loop Wire transform method. Single loop Wire transform method, we can use this method also, as well as we can solve the nodal analysis and voltage divisions. I have not shown you that those two things, but I have shown you the mesh analysis. Okay, mesh is easy, so we can solve the mesh also. We can use the mesh also for the problems. Okay, and just check this one. Uh, and multiple node method. Okay, I have not shown you just multiple nodes. Okay, I'll show the multiple node method later, the next class, but I tried to complete the mesh today. Okay, let me close the recording.